Everybody, Mr. Smith here, and in this lesson we are going to talk about equivalent algebraic expressions. So let's get started. All right, so ever since grade 9, we've been getting used to the idea that two relations or two functions can look completely different as far as their equation goes, but when you graph them, they give you the same graph. So is it really, you can copy this down in your margins if you want, but like really quickly, you might graph a line in grade 9 in y equals mx plus b form, like y equals x plus 1. But then rearranging that, you might have learned the standard form of a line x minus y equals 0. And those two different looking equations gave you the same graph. They're equivalent. Or in terms of parabolas, I'll just do a simple example. X minus 1, x plus 1. In factored form, if you expand it, is x squared minus 1. And those two different looking equations gave you the same graph. They're equivalent. So we're going to determine if these two more complex looking, and these are both quadratic, one's kind of in standard form and one's kind of like in some complex unsimplified form. We're going to see if they're equivalent, and we're going to do it three ways. We're going to test different x values, and then we're going to do some simplifying, and then I'll pop them into Desmos, and you can do it too, and we'll see what their graphs look like. So let's do this one. So I've prompted you guys to put in 0, so you can pause the video and just kind of crank through these if you want. But that'll give us minus 1 squared, and then 3 times 0, so plus negative 2. So that's 2 minus 2 gives you 0. And for the second function, when you evaluate g at 0, you get 2 times 0 squared minus 0. That's obviously 0. So 0, 0 is a shared point between both of these guys. Let's try x equals 2. So 2 times 2 minus 1 squared, we're finding f at 2. I should pop in there. And plus 3 times 2 minus 2. And then g at 2 equals 2 times 2 squared minus 2. Now, these two functions are equivalent. Whatever you plug into one, you're going to get the same in the other. So let's finish that off. So this is 2 times 1 squared. Do it in as many steps as you need to. 6 minus 2 plus 4. So it looks like 6. And yeah, this works out because 2 times 2 squared, that's 8 minus 2 is 6. So it's certainly looking like these two functions might be equivalent because they each share the point 0, 0 and 2, 6. Now, pick any number you want and see if it works out the same way. I'm going to I'll pick 7. 7 is kind of a different number. So the function is 2 for f, 2 times 7 minus 1 squared plus 3 times, 3 times 7 minus 2. That's 2 times 6 squared. 21 minus 2 is 19. That's 72 plus 19. So that's 91. So do we get 91 with the other guy? So g at 7 is 2 times 7 squared minus 2. 2 times 49. Did I do something wrong here? Probably. What's the original function? 2 times x minus 1 squared plus 3 times x minus 2. 72 plus 19 is 91. 2x squared minus x. That's why. I have to subtract 7. Because 2 times 49 is 98, and 98 subtract 7 is 91. So hopefully you at home, no matter what you plugged in, you found out that, f at whatever you plugged in is the same as g at whatever you plugged in. So we can be reasonably sure, just by trying a few points, that these two graphs are the same. Now, it is possible, it is possible that you might have one function that goes through 3 points, and then a separate function that goes through those as well, and that you just got lucky. But probably not here. But yeah, this isn't a formal way to check. Just because you've shown a few points from my diagram at the right, it doesn't guarantee they're equivalent. You can be more likely the more points you choose, but we can verify their equivalent algebraically. So that first function, the more complex looking one, f at x, was 2 times x minus 1 squared plus 3x minus 2. At least I think that was it from memory. Yeah. So let's simplify this. X minus 1 squared is x squared minus 2x plus 1. I don't really need those brackets. Plus 3x minus 2. Distribute the 2. 2x squared minus 4x plus 2. Distribute the 2. And we still have plus 3x minus 2. So check this out. We have 2x squared minus 4x and 3x give you minus 1x, and 2 minus 2 is 0. So we've just actually shown that algebraically these two guys are equivalent because one simplifies to the other. Now, finally, another way we could check, and this is 99.9% foolproof. Not quite foolproof, but can show you if you want to see if they're familiar, graph them. That gives you a good idea. So we had x minus 1 squared, and then we were adding 3x minus 2. So as you can see, it's quadratic. That's what it looks like. And our second one was 2x squared minus x. And as you can see, going back and forth between them, red, purple, they're the same function graphically. So in every way, these guys are the same. We showed it 3 ways. We tried a bunch of points, which gave us an idea, but didn't exactly prove it. We used algebra, which did prove it. And then we kind of proved it by graphing. So those are 3 different ways that you could mess around, see if things are equivalent. So these guys were equivalent. Let's look at a second example here. So I've given you 2 functions and some values to try. So yeah, let's dive in here. I think with 0, we can hopefully just shave some work off, because if we plug in 0, all this stuff with x will go away, and you have -8 over -12, which if you simplify is 2/3. And if you plug in g at 0, 0, 0, you're just left with 2/3 as well. So these 2 functions, now these aren't quadratic, these are rational functions. They look very involved, especially the first one. But so far they share a point. Let's see if they share another point. The more points they share, the more likely it is that they're the same function. So we have 2 squared minus 2 times 2 minus 8. And on the bottom, 2 squared minus itself minus 12. So let's just do this at once. So on the top, we get 4, take away 4, take away 8 is minus 8. 4 take away 2 is 2. Take away 12 is -10. So we got 4 over 5. I wonder what we'll get for the second one. G at 2 equals, plug in 2. So 2 plus 2 on top. Look at that. 2 plus 3 on the bottom, and we get 4 over 5 as well. So 4 over 5 is on both functions. They're probably equivalent. Why don't you try a number? I'm going to try 10. 10 squared minus 2 times 10 minus 8 over 10 squared minus 10 minus 12. So that's 100 minus 20 minus 8, so 72. And 100 minus 10 is 90, minus 12, 78. 72 over 78 simplifies to 36 over 39. Is that true? Those are both divisible by 6, though. So if I divide both by 6, I get 12 over 13 simplified. How about g at 10? Yeah, 10 plus 2 and 10 plus 3, 12 over 13. So I'm sure at home you made a random choice and hopefully got the same values. So our conclusion, are they equivalent? Well, the answer is like almost. It's a very strong yes with one kind of little distinction. Now, the distinction we'll get to in a second. But let's try to simplify this. So let's take f at x, the more complicated one. And it was equal to x squared minus 2x minus 8. And on the bottom, we had x squared minus x minus 12. How can we simplify this? Well, both of the top and bottom are simple trinomials that we're able to factor. The one on top, we're looking for numbers that add to minus 2, multiply to minus 8. And on the bottom, we're looking for numbers that add to minus 1 and multiply to minus 12. And we can factor both of them. On the top, it's negative 4 and positive 2. That works. On the bottom, it's negative 4 and positive 3. That works. And check this out, guys. Look at this common bracket, x minus 4, x minus 4. Now, what's anything divided by itself? What's 1 divided by 1? Negative 5 divided by 5. 10 divided by 10. It's 1, right? And we're left with x plus 2 over x plus 3. And that was the same as g at x. But I want to just add a little caveat here. Almost. And I'll explain to you why I'm saying almost in a second. Because right now, you should be thinking, well, every point we tried matched up. If I simplify f at x, or f of x, I get g of x. And then watch as I graph these two guys. Okay, so our first one is, I'm going to be careful here with brackets, x squared. Then it was minus 2x minus 8. And we're dividing that by x squared minus x minus 12. That's what that graph looks like. And the graph of x plus 2 divided by x plus 3, it's the same. So again, this is another indication that these graphs are algebraically equivalent. Almost. And now I'm getting to the point where I'm going to say, well, why are you saying almost? Because you didn't say almost with these guys. Now you're saying almost with these guys. So why? So the first pair we looked at, the two that were quadratic functions, they were equivalent in every way. The second pair, and we call those rational functions because they're functions that are one thing divided by another, they appear to be algebraically equivalent. And so here's where the almost. I want you to go back, and if you have room, or just do it on a separate piece of paper. We tried 0, we tried 2, and we tried a random number. I chose 10. I want you guys to try to plug in 4. Maybe, just maybe, when you were doing your choice, by coincidence, you chose 4, and you were kind of wondering what was happening because you would have found something interesting. But I want everybody to try 4. I'm just going to pop in a different color here, but this can be done in the margin. This can be done wherever. But yeah, this is going to illustrate why I've been saying almost. What's f at 4? 4 squared minus 2 times 4 minus 8. On the bottom, 4 squared minus 4 minus 12. So we get on top 16 minus 8, 0, which is not a problem in itself, right? But look what we get in the bottom, 16 minus 4 minus 12 is also 0. 0 over 0, you can try that on your calculator, but that's an undefined number. It gives you an error message. However, g at 4, when you plug in that one, you get 4 plus 2 over 4 plus 3, and you get 6 over 7. They're not equivalent when x is equal to 4. That's the one value that makes them not equivalent. Why x equals 4? Well, think back when we were simplifying, guys. When we factored and divided out x minus 4 over x minus 4, we used the logic that anything divided by itself was equal to 1, except one number. 0 divided by 0 does not equal 1. So this works if x does not equal to 4. So let's continue talking about that. If we talk about the domain for each of these functions, the first two, which were just quadratic functions, remember for a quadratic function, you can plug in any value you want for x. Nothing breaks down the equation, and we said the domain is x can be any real number. But with rational functions, because that they're like dividing, and you can't divide by 0, often with rational functions, there are some values that don't work. And we know what they are already, or at least one of them. So if you recall, we factored this guy. In fact, factoring is fine. There's no weird things to go on there. We got x minus 4, x plus 2 over x minus 4, x plus 3. And if we ask, what's the domain of this function? Well, with a rational function, we should be thinking, well, what x values would break the function, would break it down, would not work? Well, it's things that make the bottom 0, because you can't divide by 0. And so in this case, the domain of this function would be x can be any real number, except x can't equal 4, and x can't equal -3. Because if you plug those values in, you would get a 0 on the bottom, and you can't divide by 0. The function for g is x can be any real number, but for g, the only problem value is -3. So they are slightly different in one way. They're algebraically equivalent for every value except x equals 4. So how do we kind of write this? Because we could, as we saw, we could simplify the first function. F at x was x squared minus 2x minus 8 divided by x squared minus x minus 12. We'd like to be able to simplify things, but how do we take care of it and just make sure that we're being 100% correct? Because just saying f and g are equal isn't quite true, because 4 makes them both different. So as we saw with some factoring, that f at x could simplify to x plus 2 over x plus 3. But here's where we just do a small difference. Yeah, it does simplify to that, only if x doesn't equal to 4. All right. So, and actually, I'll throw in here too, x doesn't equal to -3, because both of those things don't work in the bottom. So f at x doesn't quite equal g at x. F of x equals what we have for g of x, except for one value. X doesn't equal 4. And this is the one thing we kind of have to get used to with rational functions, is that sometimes there's restrictions. And that sometimes means that two rational functions aren't quite equal. They might be equal except for one or two values. So it's a little something to wrap our minds around. So let's take this rational function and let's simplify it. And let's state any restrictions for this one. So a common theme with simplifying rational functions is like factoring. Because right now, it doesn't appear that anything will divide out. But we can factor the top. There are numbers that multiply to 10 and add to 21. Those numbers are 3 and 7. On the bottom, we have x plus 3. And we can now divide those, and we get x plus 7. But guys, that division would only work if x wasn't equal to minus 3. Because if it was minus 3, it'd be 0 over 0. And you guys can see, too, that if you plugged in minus 3 up here, you get 0 on the bottom. So this is an example of how we would simplify a rational function. Factor, you see if there's anything you can divide out. And then you, as a restriction at the end, you write down any value of x would make the bottom 0. So this is called a restriction on the domain, or we just often say it's a restriction. Just as an aside, this is kind of cool. I'm going to go back to Desmos. I'm going to graph that one. What would that graph look like? That messy x squared plus 10x plus 21 divided by x plus 3, I think it was. When you graph it, it just shows up as a line, which is so cool. Well, that's because we just showed it's actually equivalent to a line, except for the one value at minus 3. It's really neat. Let's try another one. So this one has a complex trinomial over another complex trinomial. Now, keep in mind, we're not going to be doing pages and pages and pages of factoring complex trinomials, but they come up from time to time. You're going to have to be able to handle them when you get to your calculus course. So we'll do an example of handling them now. And it's not so bad, actually. I mean, ultimately, we have to factor each one of these guys. So we'll factor each one kind of quickly on the right here. So we're looking for this guy, numbers that add to minus 7 and multiply to, it's a complex trinomial. So that'd be minus 30. 6 times minus 5. Use decomposition. So I can see that my two numbers would be 10 and, so it would be 3 and negative 10. So 3x minus 10x minus 5. Common factor of the first pair, common factor of the second pair. It's 3x, and we're left with 2x plus 1. I can take out minus 5 from this pair. Also left with 2x plus 1. That's good. And then I don't know why I'm underlining that. And then we're left with 2x plus 1 as a common bracket with 3x and minus 5 left over. So the top would simplify to 2x plus 1 times 3x minus 5. How about the bottom? Let's factor it below. So 3x squared plus x minus 10. We're looking for numbers that add to 1. Multiplied to minus 30 also. That's just a coincidence. Those numbers I can see would be positive 6 and negative 5. And I can take 3x from the first bit. I'm left with x plus 2. And if I take out minus 5, yep, I also have x plus 2. And this factors into, I'll say x plus 2 times 3x minus 5. So the bottom goes to x plus 2 times 3x minus 5. And look, we have two brackets, 3x minus 5 times 3x minus 5. We can divide those out. So the function g of x is equivalent to 2x plus 1 divided by x plus 2 with two restrictions. One, x can't be negative 2. We can see that because that would make the bottom 0. But something else would make the bottom 0 too in the original function. And that's whatever makes 3x minus 5 equal to 0. And just as an aside, many of you guys could probably just mentally do this, but I'll just show the work. What makes 3x minus 5 equal to 0? Well, what makes 3x equal to 5? It's 5 over 3. So we write these, in this case, we have two restrictions. So we simplified to 2x plus 1 over x plus 2, and we wrote down our restrictions, whatever makes the bottom 0. That's a pretty heavy one. That's basically as hard as it's going to get. And again, I won't be having you do pages and pages of these. But like if we just kind of reflect on it, we just did complex trinomial factoring, which, it was a grade 10 topic and we've reviewed it. And then we just did a division, divided those like brackets out. So, not crazy unreasonable for you guys to do this. It would be unreasonable for me to make you do like 10 of these in a row or a lot of them on an evaluation, but I do expect you guys to be able to do this kind of problem. All right. One little simple application problem. Here we have a square with a side length of 7 centimeters, and it's being cut out from a larger square that has some side length of x. And I've drawn it that the square is cut out this way, but the square could be cut out like here or anywhere else. This is the way I drew it. So just a square is cut out. Doesn't matter how the square is cut out. Let's do A. A is kind of like an exercise from your grade 9 math course, actually, an expression for the area of this function, because the area of the shaded region is like we just have a bigger square and we're subtracting a cutout of a smaller square. The area of the big square is x by x, or x squared, and the area of the small guy is 7 by 7, or 7 squared. So a function representing the shaded region is just x squared minus 49. How does this connect to equivalent algebraic expressions? Well, in part B, you're asked to write the area function in factored form. This is the difference of squares. I could just write that as x minus 7, x plus 7. It's a different looking expression, but it's the same function. So it's equivalent. It's an equivalent algebraic expressions. Let's talk about the domain in this one. This one's not rational functions, so we're not worried about what makes the bottom 0. With polynomials, nothing makes any, there's no bottom, right? So nothing makes the bottom 0. But there are some restrictions here. And it's this. This is where the restrictions come in. A function, or an area, can't be negative. An area could be 0. I could say like I have 0 space left over in my room or whatever, but I can't say I have -5 square feet of area, or the area of this garden is -10 meters squared. That doesn't make any sense. So we are restricted here. There is a restricted domain, and to illustrate that, I might just make a rough sketch here. So x, I might just change that up a little bit. No, I think, yeah, I will change it actually. Do that. X-axis, but I want to draw my y-axis kind of like this. So what does this function look like? X minus 7, x plus 7. So that function looks like this. If I was just to graph it, it's a parabola. It opens up, and its zeros are at -7 and +7. So guys, let's think about this. Can the side length of x be a negative number? So obviously, no, that's like silly, right? You can't have negative numbers. But can x be any positive number? Can you have this green square be like 1 centimeter by 1 centimeter and then cut out a 7 centimeter square? Like, no, that's silly, right? And it's illustrated on the right here. Up until 7, the area function is below the y-axis, right? So up until 7 and beyond, the area would be negative, which is not good. You need an area bigger than 7 in order to, or a length bigger than 7 to make sure so that it's bigger than your square cutout, right? Like if your square cutout is 7 centimeters, then the thing you're cutting it out of, it better be bigger than 7 centimeters on one side. So the domain for this function is x can be any real number as long as x is greater than or equal to 7. Technically, if it was 7 centimeters, you'd be cutting out the entire thing. So that's just nothing there is like crazy complicated in terms of factoring from your grade 10 course. But thinking about what the domain would be is a bit new because, we have a polynomial or a quadratic function, and we're not used to having restricting the domain for that, but often real life does restrict the domain. So just a fun little exercise there. So what should you guys be able to do? If you guys can come away from today knowing how to first, take, if you have two expressions and you're asked to see if they're equivalent, be able to, expand or simplify or factor, and then be able to see if they're equivalent or not. You guys also now need to get into a frame of mind where if you have a rational function, you need to be thinking, what makes the bottom 0? Because we simplified the one on this slide and got x plus 2 equals x plus 3, except for one value, 4, right? So the function f was equal to the function g, except for that one value at x equals 4. So you guys have to get used to being able to simplify functions like f and state restrictions. And what that looks like is our two examples here. Factor the top and bottom. Once you're done, write out the values that make the bottom 0. In the example A here, it was -3. In example B, the factoring took a bit more work. And then there was 2 restrictions because 2 things made the bottom 0. So that will require a bit of practice on your end. What we're building towards is right now is just building up a skill set, a toolbox on actually working with these rational functions, because you need this skill for the grade 12 functions and calculus course. We'll do these skills over a few days and then we'll kind of be done with them. But this is the part of the course where we introduce those skills with the intent purely just to get us ready for grade 12. In later lessons, we're going to take rational expressions. We're going to actually add and subtract them. We're not going to divide them. That's actually a typo on my part. Just adding, subtracting, and multiplying. No, wait, we will divide them. Never mind. Keep that in there. We will divide them. That's for another lesson, guys. Until then, I hope you're doing well. Have a great day, and we'll see you soon.